Welcome to the Solid State Physics presentation on creating a DIY FCC crystal using a common household material, which is salt. My name is Nur Jamila binti Nur Azlan, and today I will guide you through an experiment that demonstrates the principles of crystal formation and the fascinating structure of the face-centered cubic lattice of sodium chloride. For this experiment, we are going to use simple, everyday materials that we can easily find at home. Each material plays a key role in helping us create and observe the face-centered cubic lattice structure of sodium chloride. First, we need non-iodized salt. It is important to use non-iodized salt because iodized salt contains additives that might interfere with the crystallization process. This ensures that our crystals will form properly and with their natural cubic structure. Next, we use hot water. Hot water acts as a solvent to dissolve the salt efficiently, allowing us to create a saturated solution. The temperature of the water helps increase the solubility of salt. Let's move on to the procedures. Begin by adding 40 grams of non-iodized salt to 100 milliliters of hot water in a container. The hot water helps dissolve the salt more efficiently. Secondly, using a spoon, stir the solution. Continue stirring until no more salt can dissolve, indicating that the solution has become saturated. Next, filter the saturated solution to remove any undissolved salt particles. This ensures a uniform solution for crystal growth. Finally, pour the filtered solution onto a clean tray or plate and leave it undisturbed in a well-ventilated area. As the water evaporates, you will observe the formation of cubic salt crystal. After a few days, here we can see the result of our experiment, the formation of small, well-defined sodium chloride crystals. These crystals are a perfect representation of the underlying atomic structure of NaCl. These physical characteristics, cubic shape, sharp edges, and clarity, are directly connected to the chemical and atomic properties of sodium chloride. The evaporation of water during the experiment allowed the ions to come together and align perfectly, forming these beautiful cubic crystals. So, how does sodium chloride crystal form? In the first step, sodium chloride dissolves in water, dissociating into sodium and chloride ions. This creates free ions in the solution that will later form the crystal. Next, when the solutions become supersaturated, the excess sodium and chloride ions begin to aggregate. These ions form a nucleus, which acts as the starting point for the crystal's growth. As the crystal grows, the sodium and chloride ions alternate in a regular 3D arrangement. This structure minimizes energy and forms a face-centered cubic lattice. In this lattice, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions, creating a stable structure. Finally, the crystal grows layer by layer along specific crystallographic planes. This results in a cubic shape with sharp edges and flat face, characteristic of sodium chloride crystals. Next, let's introduce you FCC unit cell. In FCC unit cells, atoms are positioned at all 8 corners of the cube. Each corner atom is shared among 8 neighboring unit cells. This means that only 1/8 of each corner atom belongs to a single unit cell. In addition to the corner atoms, an atom is allocated at the center of each of the 6 faces of the cube. Each face-centered atom is shared between 2 adjacent unit cells. As a result, only 1/2 of each face-centered atom is part of one unit cell. In the FCC structure, each atom is surrounded by 12 nearest neighbors. By adding the contribution from the corners and the face, the total atoms in an FCC unit cell is equal to 4 atoms. The atomic packing factor, or APF, represents the fraction of the unit cell's volume that is occupied by ions. It helps quantify how tightly packed the ions are in the lattice. For a face-center cubic lattice like sodium chloride, the APF is calculated as the volume of the ions in the unit cell divided by the total volume of the unit cell. The result for FCC is 0.74 or 74%, meaning 74% of the unit cell's volume is occupied by ions, while the remaining 26% is empty space. This high packing efficiency is due to the close packed arrangement of ions in the FCC lattice. Each ion is surrounded by 6 oppositely charged ions, ensuring the structure is both compact and stable. A high APF contributes to the stability of the NaCl structure by minimizing void space and enhancing the ionic bonding strength between sodium ion and chloride ion. Thank you so much for watching this video. I hope you enjoy learning about the fascinating process of crystal formation and the unique properties of sodium chloride.